for the next presentation. Gina Sitaraman has created this presentation on Affinity. Affinity is a complex topic, and there's many different ways to tackle it on these computing systems. And so you're going to see quite a bit of complexity involved with how to place things. She's worked hard on this, and it's a little bit different on each platform. So thank you, Gina, for working on updating this presentation. Turn it over to you.
Thank you, Bob. I thank you for the introduction. I'm Gina Sitaraman, and I work with Bob and others at AMD, optimizing HPC applications on our hardware. I have a lot of fun doing that. I feel like I play a small part in advancing scientific discoveries because I get to work with researchers like you and on your applications and making a difference in this world. So at AMD, I have learned a lot of things from mentors like Bob and others. And in this presentation, I'm getting an opportunity to share some of that learning. And I hope that these, whatever we present here, is going to be helpful in your optimization journeys. So Bob has been instrumental in putting this material together. We today are going to talk about Affinity, what it means, and how it can help our applications. So, sorry, I'm struggling to advance the slides. So, okay. All right. So, in addition to Bob, there have been several others who have provided material for this presentation. I want to call out Tom Papatheodore from Oak Ridge National Labs because he gave me permission to use some of his code, some of the code that's public, but I'm able to use that because I find some of those very useful, and I hope the same for you. Marcus Wagner from HPE and Alfio Lazzaro from HPE as well. They've provided scripts that I use in my job here, and we're sharing those. And of course, a lot of people from AMD, George, you all know, and we have others, Bill Brantley, Noel Chalmers, and KJ, who've helped us put this material together. So the agenda for today, we're going to take a look at what modern architectures look like. We are going to focus on LUMI and what LUMI's topology looks like. I think you've already seen this many times, but we're going to do it again, so you never forget it. And then look at what is Affinity and why it is important, and some tools that will help us understand node topology. And then what are some placement considerations when we look at LUMI nodes in particular? What do we want to think about when we run our applications? And then some case studies, because like Bob mentioned, every machine is different, and how to set affinity for CPUs and GPUs seems to differ. Every day we log into a machine, it seems to be different. So today we're just going to see one example or a set of examples, but if things don't work, we have man pages to help us figure out what might be going on and find the right settings for the system at hand. So most of this learning can be applied to other systems as well. So in that spirit, let's go ahead and take a look at modern architectures. What does that involve? What do they have? They are increasingly complex, right? We have multiple resources, such as multiple sockets, many cores, many GPUs on a node, several memory controllers, several network interface cards, and where they are placed, etc. And we also have, we have peripherals and memory controllers, for example, and GPUs. These are local to different CPU sockets. These are um, uh, some of the complexities that come with modern architectures. And you know, normally the operating system controls process scheduling, but the operating system is not designed for high performance computing jobs and parallel jobs. So what might happen is we spawn processes, but they may get preempted for another higher priority process, or for whatever reason, the operating system makes some decisions. And when such preemptions and rescheduling happens, the data that was cached for that process has to be moved from one set of caches to the caches that are closer to the new core where the process is going to run next. So the operating system is unaware of parallel processes or their threads. So this is what we have today. So when we take a look at the Lumi node, you've seen this diagram before. We have borrowed this diagram from the Frontier user guide. So because Lumi nodes are very similar to Frontier nodes, and so let's take a look at some of the salient features. So the main thing, the first thing that we see is that we have one socket with 64 cores, CPU cores in that socket. That is the CPU socket, CPU. There's one CPU. And then we also see these four big rectangles. These are the four MI250X GPUs. Here we have a closer look at the MI250X GPU. The GPU itself consists of two graphics compute dies, which we will refer to as GCDs, that are connected by four high-speed Infinity Fabric links. Each GCD also has 64 gigabytes of high bandwidth memory, and with a peak performance of 1.6 terabytes per second. All right, so we have four of those GPUs on this node. And between the GCDs, we saw there are four links, but we also see that between different pairs of GCDs, there are different number of Infinity Fabric links. So for example, GCD4 and GCD2 have two of these links connecting them. But when you look at GCD2 and GCD0, there's only one link connecting them. So the speed on these links is, for each link, it's 50 gigabytes per second or in each direction, right? So when we have four links together, that makes 200 gigabytes per second in each direction. Okay, and next we divert our attention to the memory here. On the node, we have DDR4 RAM that is 512 gigs in total. And putting together all of the GPU memories, that's another 512 gigs of GPU memory. So CPU memory is 512 gigs. And similarly, we have the same amount aggregate memory of 512 gigs on the GPUs as well. And the other thing that we want to remember is that there are four network interface cards on each node, and that these NICs are connected to odd numbered GCDs. So this is the top level view of a Lumi node. We are going to go into more details about what all this is in a little bit. So, but before that, okay, so in that picture, we also see that there's something called a NUMA. NUMA 0, 1, 2, and 3 mentioned there. So what are those things? What is NUMA? NUMA refers to non-uniform memory access. And in multiprocessor systems, resources are divided into logical entities, and that is what we call as NUMA domains. So NUMA domain is a grouping of cores, memory, and other peripherals, the various resources. And in this kind of a multiprocessor system, each CPU core is attached to its own local memory, while being able to access the memories of all the other processors. So what happens with this setup is that local memory accesses, so if from cores, if you access memory that is local to them, that would be, those accesses are fast. Whereas if we were to access data in other NUMA regions, then those accesses will be slower. They have a higher latency. And especially if you, here we have only one socket, but if we have a system with multiple sockets, then reaching memory that is closer to another socket takes even longer because you have to then cross the socket to socket interface. And so with local access, there's also another benefit. We reduce the contention from CPUs. We are only having a limited number of CPU cores reaching for data in some of the memory sticks. So that way we reduce contention, and that helps in increasing bandwidth, the achieved bandwidth. Another thing we want to point out here is each physical core, we have 2 hardware threads running on them. So for example, here, physical core number 6 has hardware thread number 6 and 70. And another thing that I want to point out is here we see there are 8 cores. All of them are sharing the same L3 cache. So we have 8 such sets of 8 cores. And each of those sets share L3 cache. So that has some benefits we will see later. So NUMA configuration. So there are many ways in which we can configure NUMA on our systems. On Lumi, there are only 2 possible ways, one NPS 1 and NPS 4. They are configured at boot time. And the most important thing for us to remember is that the site administers this setting and we cannot change it. So I believe at the moment, we have Lumi nodes configured with NPS 4. So what is the difference between NPS 1 and 4? So the difference is how many NUMA domains we have per socket. So in NPS 1, we have 1. NPS 4, we have 4. So when we have just one NUMA domain in a socket, say we have 8 memory channels, what happens is all of your memory accesses are going to be interleaved across all of these 8 memory channels in NPS 1 mode. So it gives us more uniform bandwidth no matter which core you are accessing that data from. It is more tolerant of hotspots as well. And there are benefits to using NPS 1 in some cases. For example, if you're just running one task, one MPI rank, you may benefit from a higher CPU memory bandwidth because now you're able to use all of the memory controllers for this one task and read data faster, right? But in NPS 4, we have 4 NUMA domains per socket. So of the 8 memory controllers, each NUMA domain is associated with 2 memory channels or 2 memory controllers. So all the memory accesses are going to be interleaved across 2 channels instead of 8. And so this helps us because of reduced contention. We can get a higher memory bandwidth due to and also lower latency because these memories will be local to these cores, this set of cores, all of them belonging to the same NUMA domain. But we may be vulnerable to hotspots. What if we do not use all the cores in the system? Then we are going to have some hotspots in some of those memory channels, right? And this is the reason why Affinity is really important. We're going to see what it is. But in NPS 4, which is the setting we have on Lumi, it is really important to pay attention to Affinity. Also, to spread processes across all the NUMA domains, use all the resources as evenly as possible, if that makes sense for your application. Okay, what is Affinity? So Affinity is a way for processes to indicate preference for hardware components. So I'd like to use these memory controllers. I'd like to use these cores, and I want to use this NIC, etc. So typically, processes are pinned to resources belonging to the same NUMA domain for all the reasons we saw earlier. Again, a repetition of what we saw. Why is Affinity important? Because we would like to reuse cache. We would like to improve memory locality. We want to reduce the contention for resources. That helps us lower latency. And another benefit that we get from setting Affinity correctly is variability between runs is also reduced. So where is Affinity important? Is it important for jobs running on the CPUs or GPUs or what? So because NUMA domains are, it's mostly extremely important for processes running on CPU cores and the associated memories. When running on GPUs, Affinity is less critical unless we have a bottleneck with the data placement on host memory. So what do I mean by that? If okay, so Affinity is also, so NUMA domains also associate GPUs with CPU cores and memory controllers. All of them are one logical entity. So if we have memory copies between host memory and the device memory, in order to get the maximum bandwidth or utilization of the bandwidth um, of those transfers, we would like to use the same GPU and the CPU cores that belong to the same NUMA domain. If we have page migration and direct memory access, we also want to be as close to the memory as possible because remote memory accesses can be quite expensive. So other than that, within a GPU, Affinity is not that important. So when I say Affinity, I'm thinking I might use some other terms interchangeably. I might say pinning processes and their threads to cores, pinning or binding. But Affinity is more than just binding. It can involve placement and order. And let's take a look at what those terms mean. Placement refers to where the policy of where a process is going to be placed. So what we mean by that, let's look at some examples that motivate the need for proper placement. The main motivation is that we want to maximize the use of all available resources for a particular application or workload. We want to use all the resources, maybe that is one case. Your application may have to run with many processes that have multiple threads, like a hybrid process that uses multi-threading on the CPU and then uses GPU for offloading compute. And in that case, you may want to have separate cores for each thread because you don't want to have contention between different threads of your process. It depends on the application. Or in some cases, you may not want to use the second hardware thread that's running on a physical core because they have to timeshare, and you may not want that. And in some cases, you may not have enough memory, or maybe you want to maximize the use of cache in the CPU, the CPU cache. So in some cases, we may want to skip some cores. Like in a NUMA domain, we have 16 cores. We may not want to run on all of them, perhaps. We may also want to reserve some cores for system operations, and that is done to reduce jitter for timing purposes and to reduce variability, like we just saw. So we're going to take a closer look at this particular thing in a little bit. And also, okay, when we are running MPI applications, MPI prefers gang scheduling, but the OS doesn't know that these processes are connected. So when we have a synchronization barrier, if one of the processes is getting rescheduled by the OS, all the other processes in the same ring are waiting at that synchronization barrier. So we would like to avoid such situations. So Affinity helps. That way the OS does not reschedule processes or their threads. Until the last decade, this placement was not that important. We only had a few cores in a CPU. We had more uniform architectures. We didn't have GPUs. We had either shared or distributed memory systems. And the OS controlled placement, and that was fine. But today we have to pay attention to controlling placement. And again, the reasons are we do not want to oversubscribe compute resources and reduce contention. We also want to avoid non-uniform use of resources, where some of the resources are in use, some of them are idle. We don't want that situation. And we also want optimal communication performance. And we'd like to definitely avoid migration of processes by the OS. The good thing for us is that, okay, I see a message. I'll get to it. The good thing for us is that affinity controls in the operating system and MPI have greatly improved and changed. So different MPI implementations have different affinity controls. And today we are just going to see what Slurm bindings in Cray and Pitch provide to us using some examples. So Bob, if I need to answer some questions, would you please interrupt me for now? I'm just going to keep going.
I'll try to answer these.
Okay, thank you so much. Okay, and then we saw placement, where the processes are placed, but the next concept is the order. So we have a parallel job, we have many ranks. How do we order those processes such that they are distributed evenly across the sockets, and also, very importantly, processes communicating the most with each other are close together, so we reduce latency and achieve a higher utilization of the bandwidth. So load balancing heavy workloads is also very important. So different MPI implementations have different default orderings. For example, these are some very commonly used ones. So like round robin, processes are distributed in a round robin fashion. Like if we had 2 sockets and there are, for example, 8 MPI ranks, it schedules rank 0 on socket 0, rank 1 on socket 1, and goes back and forth between the 2 sockets. This is round robin scheduling or ordering of these MPI ranks. Round robin ordering is good because we can then maximize available cache for each process and then evenly utilize the resources of a node. We are balancing across all the resources we have. In the packed or close case, we try to use all the resources in one socket first, fill it up, and then go to the next socket. So we want to pack things together. In some cases, that is useful. For example, let's take the same example, 8 MPI ranks, and we have 2 sockets. We are taking a really simple CPU here, like we only have 4 cores in each CPU. We are going to schedule ranks 0, 1, 2, and 3 on socket 0 first before scheduling the other ranks on socket 1. This is an example for packed ordering. And this may be important because if ranks that communicate the most are accessing data in the same memory node, and they are able to share cache, and especially when we have this hybrid application, which is using multi-threading, a process and its threads, it's better if they are running on cores next to each other, because that way they can share the cache, CPU cache, and achieve a higher bandwidth of communication. So before I get into the next section, what did we see? We saw what the Lumi node topology looks like, and what affinity is, what NUMA domains are. Affinity consists of binding, placement, and order. And we saw a high-level view of what all those things mean. Next, we're going to go into understanding node topology and what kind of tools do we have at our disposal for doing that. So when we get on a new system, we would like to understand what's on that system. So even on a Lumi type system, the configuration may be different. We had a big upgrade recently. I could not log in until this morning, so I haven't had a chance to see if something has changed. Much of the material that I have put together here um, is based on what we had in February, at the end of February. So um, I'm not sure. So this may be very, very true. Something might have changed. That is something that I'd like you to go back and check using these tools. So what could have changed? We may have a new NUMA configuration on the system. We may have changed to NPS1. I don't know, right? Or some physical cores may have been reserved, which is the case in Lumi. One core is reserved for system operations. We may or may not have hyperthreading enabled. So instead of 128 cores or hardware threads, you may just have 64. So on any system, these things are going to be different. So how do you know what you have? There are different tools, and we're going to take a look at each one of these more closely. Let's go to the first one, LS Topo. LS Topo, I believe. So it comes from the HWLock package. And that helps us visualize the node architecture. And just to get more details about the CPU, we use LSCPU. NUMA control -H, it shows the NUMA configuration on your node and what CPU cores are in each NUMA domain. And also to understand how the GPUs, the affinity for GPUs and in NUMA domains is also, you can obtain that using ROCm SMI show topo. Okay, so LS Topo. This tool is actually very useful to see to visualize your system, the topology of your system. You also have a text-based output from this tool, but if we had the out.svg or some other format, there are many different formats you can get for this diagram. If you provided that as one of the parameters, you can get a diagram like this. And on Lumi, here we first see that the entire node, this is the whole machine, and we see that there is one package. That just tells us that there is one socket on the node. And in this one socket, we have 4 NUMA domains. So we have NPS4 configuration, right? And okay, and that's okay. And then there are further details for which we really have to zoom in, right? Zooming into one of those NUMA domains, we see that, okay, we're looking at NUMA domain number 1, which is the second NUMA domain. We see that there are 2 sets of 8 cores. We also saw that in the topology diagram representation earlier. 2 sets of 8 cores, and each one of these sets is sharing this L3 cache, which is 32 megabytes in size. So there are 2 L3 caches. Another thing we see is that each one of those physical cores has 2 threads running on them, right? The threads are also enumerated, hardware threads. And then there are 2 GPUs or GPU devices in each NUMA domain. In the case of Lumi, these are 2 different GCDs. And there is one NIC because we have 4 network interface cards connected to odd number GCDs. So in each NUMA domain, we have one of those network interface cards. When we look at LSCPU, here is a condensed output from this tool. LSCPU tells us about the CPU architecture, the instruction sets that it can supports. And so the first thing when I take a look at this output is I look at, okay, how many sockets do I have? How many cores per socket do I have? And do I have hyperthreading enabled or not? If I see 1, that means hyperthreading is not enabled. If we see 2, that means it is enabled. The next thing is, okay, so total number of hardware threads, that's 128. That is what the operating system is going to see. And we also see information about the NUMA configuration. we have 4 NUMA domains in this socket, and over here we see the list of hardware threads that are associated with each NUMA domain. The same information from another tool looks more verbose. Here, NUMA control can just enumerates all of the different hardware threads. So we have 2 sets of 16 hardware threads associated with NUMA domain 0. So that's node 0, and so on. And it also prints node distances. These don't have any units. It's just a measure of how far away these cores are from each other. It's this output particularly is not very interesting, but if you had a system with multiple sockets, the node distances may be more interesting. Now that we understand what CPUs we have, let's look at what GPUs we have, GPU devices, and how they are associated with the different NUMA domains. So in this example, we have all of these. Each GPU device is a GCD in a LUMI node. And this is a snippet, a simplified diagram of one of those NUMA domains from the topology diagram we saw earlier. And we see that there are 2 sets of 8 cores, right? 8 cores, each sharing an L3 cache belonging to one NUMA domain. We also see that there is a high-speed fabric link connecting each of these core sets to a GCD or a GPU device. So in this case, for example, cores 0 through 7 are close to GCD 4, and 8 through 15 are closer to GCD 5. And that is what we see here. So NUMA node, in NUMA domain 0, we have GCDs 4 and 5. It's slightly different from other topologies you may have seen. So when we get on a system, now we know how to understand what we have, what hardware we have. Let's take another look at the LUMI node topology and some of the placement considerations that we may want to pay attention to. You see, each GCD is connected to a set of 8 cores, and thereby a particular NUMA domain via a high-speed fabric link. That's this one. And we're going to take a closer look at all of these. The second thing that we have in this topology that is unique is between 2 GCDs of the same GPU, we have 4 infinity fabric links, right? And then we also have NICs connected to odd numbered GCDs. And the other thing that we haven't spoken about yet is we can have multiple processes running on the same GPU device. On the same GCD, you can run multiple processes. That is supported natively in AMD GPUs. And so given all of these features in the LUMI node topology, we have to ensure that rank order and placement is done carefully so that we optimize communication. So let's take a closer look at each one. In this case, the fact that we have a high-speed fabric link between a GCD and one set of 8 CPU cores, it's important. Like if a process is using GCD4, it's important that it runs on one of these cores, because that way the efficiency of device to host and host to device transfers is improved, because you would be accessing memory locally. And the interesting thing is that if you were using device 0, GCD 0, you have to make sure that your process runs on one of these cores in the range 48 through 55. So the optimal mapping for CPU cores and GPU devices is different. So here we see the different number of links and the speeds they provide. So different GCD pairs have the bandwidth of transfers between those pairs is different. So um, it, it is good if we placed ranks that communicated the most on GCDs of the same GPU, because then we can make use of the higher bandwidth, right? What we show here is the peak bandwidth, and the one of the important things is that we see different bandwidths between different pairs of GCDs, but the thing to remember is that communication between buffers in GPU memory is going to be at least as fast as communication using host buffers or data stored in host memory. So the thing to keep in mind is we want to place pairs of ranks that communicate the most on GCDs that have the highest bandwidth of transfers that are on the same GPU device. When it comes to network interface cards, these are important when we have inter-node communications. On a Lumi node, we have 4 of these NICs, and they are directly connected to GCDs, odd number GCDs. So we would like to use GPU-aware MPI. So any data that is kept in device buffers, if used for MPI communications, that's going to be more efficient. It's going to have lower latency and improved performance of those MPI communications. So we stress a lot. We stress GPU-aware MPI communications a lot. Using GPU to GPU communications is important. And okay, so we also see that each NIC belongs to a different NUMA domain. So if you're running processes on a particular NUMA domain using GCDs from that NUMA domain, then you may also want to use the network interface card that is closer to that also belongs to the same NUMA domain. So I believe HPE provides environment variables. In the Cray environment, there is something that we can set up. I do not have those details, but I can find out for you. So this variable, once set, it can automatically route your traffic through the correct NIC, the NIC that belongs to the same NUMA domain. So finally, we see that, okay, we can run multiple processes on the same GPU device. This is supported natively by our GPUs. So in that case, for example, here we have 4 MPI ranks, all of them running on this GCD4, right? We would like to make sure that all of those MPI ranks run on cores that belong to this set of cores that are closest to GCD4. So depending on the application's communication pattern, you may want to pack ranks that communicate the most on the same GPU device and have them run on the CPU cores that are closest to it. So in summary, we want to choose rank order carefully because we want to optimize communication. We also know that this is true everywhere. Intra-node communication is faster than inter-node communication. It is the application expert, the domain expert, who knows the best placement for their application. For example, in a stencil code, you may want to have near neighbors placed next to each other because they communicate the most. So rank order is so important. What is really nice is HPE's CrayPat profiler has an option that can be enabled to detect communication pattern and write out something called a rank order file that can then be supplied in the next run to Cray and Pitch. And that way the ordering can be modified according to the communication pattern in your application. This is something that you may find it interesting to experiment with. HPE also has a grid order utility, but for both these tools, I would recommend that you check with HPE for more details if you're interested. In our examples today, we are going to look at some Slurm binding options. Okay, so we're going to look at examples to see how to set affinity, but how do we verify that we have the right affinity? There are several ways we can do that. Something really simple is when your application is running, you can use top or htop to visualize where they're running, each process and the process's threads. Htop is seems like a more um, nicely visualized tool. In top, to find which core a process is running on is just, it takes 2 or 3 extra steps to find, because that is not listed by default in the top output. So you have to select a column that shows the physical core that it's running on. If we were using OpenMPI, this MPI run has an option called report bindings that we can add. So when the job starts to run, OpenMPI first prints the binding information and then runs the job. So that is useful. We are not using OpenMPI here. It can be useful in other systems. For MPI and OpenMP, just multi-threaded programs and hybrid programs, there is so these are the two things that we are going to see in use in both your in. I believe the first one you're going to try to do it in the exercises, and the second one we are going to see examples here in this presentation. These two I have borrowed from Oak Ridge National Labs public repos. These two are public. They have given me permission to use this for this training. So what they do is, this is a programmatic way of finding what core the CPU thread is running on, what GPU device this process is using, etc. A similar script is HPE's XTHI script. There's a link to it. They all do the same thing. And in here, we at the end, I also have listed Bob's book titled Essentials of Parallel Computing. In chapter 14, he discusses in detail the same topic, and there are examples, many different types of examples: serial code, hybrid code, just multi-threaded code, and so on. And we have a GitHub repo to go get those examples and use them. Right. So the best practice is use one of these programs, one of these examples in your Slurm batch job. When you set up your run for your application, set up a run of one of these codes just before running your application with exactly the same configuration of the job, etc. That way, when we run it from the same batch script, it's going to print the affinity first, and then your application is going to run with the same settings. So hopefully that is an easy way for you. Every single time your job runs, you have some output that you can go back and check whether you got everything right. I do this all the time. Okay, a small detour before we go into some case studies. So what is low noise mode? We've heard of low noise mode on Lumi. Let's see what is happening here. This is NUMA domain 0, and I see that the first core set only has 7 cores. Core 0 is missing. The second core set has 8, and all the other NUMA domains have 8 plus 8 cores. So what's happening here? It so happens that Lumi administrators have set aside core 0 for system operations to deal with interrupts and etc. etc. And the reason why this is done is to reduce jitter and variability from run to run. And this is called low noise mode. If you look at this output only shows there are still 64 cores on this machine, but on the CPU, but we only see 63. That is because we ran ls topo under Slurm, and this is a Slurm setting. And so ls topo output shows 63 cores, but we have all 64. The operating system sees all 64, right? So this low noise mode may be okay for applications that are just bandwidth bound or um, GPU bound, and if they're not multi-thread, if you don't need to use all the cores, then it's not a big problem. But if you are running a very CPU intensive application that needs all cores available, then this losing one core will hurt performance. Um, and in one of the examples I'm going to show, I'd like to use all the cores, but I cannot because one core is reserved in only one of the core sets. So I have to just turn off at least one core in each of the core sets so that I can have a balanced resource assignment for all of my MPI ranks. So, so this is low noise mode. Let's keep that in mind. The first core 0 is not available. So you'll see it in the output uh, that we are going to run. So we are going to move into the case studies, and I have examples for two different cases. One is serial applications that use only multi-threading with OpenMP, and MPI applications that have OpenMP on the CPU side and HIP for offloading compute on onto the GPUs. So for the serial case, we're going to see three different ways of setting affinity. The first is using NUMA control. Um, and then we will look at some OpenMP settings in the form of environment variables for setting affinity. And then different OpenMP implementations may offer different things. So we are going to see an example of what the GNU OpenMP implementation offers. And for the case where we have multi-threading on the CPU and offload to GPUs, where we use HIP, we're going to see some examples of Slurm binding options. Okay, so in the case of the serial application and just multi-threading on CPUs, it's important to set CPU affinity correctly. And NUMA control is one of the tools that we have from libnuma-dev Linux package. In some systems, I have also seen that there is a package called NUMA control that provides this tool. So after installing one of those packages, we can use NUMA control to set the NUMA policy for processes and their threads. So in this case, for example, exe is our serial application. And here we are saying, please run that application on one of these cores that I've given you, that is cores either 2 or 3. And also interleave, allocate all of my memory on NUMA node 0. Right. And in the second example here, I have the same serial application. I only need one core, but I'm giving you a range of, from 1 through 7 hardware threads that you can run this application on. Schedule it on one of these cores, but also make sure that all of my data accesses are interleaved across NUMA nodes 0 and 1. Right. So this is just like a drop in the ocean. There are so many options that we may be able to use. So it's always best to go and look at the man page. And once we have the application running, it's easy to just run htop or top to see where it's running. So when it comes to OpenMP, they have a very, very rich specification to control affinity settings. The options are very well documented. And I'm just pointing out a few environment variables. There are a couple at the bottom that seemed interesting, but mostly the first two are what we need. So OMP places, that is a way in which we can indicate what hardware resources we want to use. So where we want to place these processes and their threads. So these OMP places can be set up with one of these abstract names. For example, cores or threads, place my processes on different sockets, or L1 cache regions or L3 cache regions, etc. So the definitions are going to be implementation specific. So you may have a different list of options that you can provide to OMP places depending on the OpenMP implementation that you have. Now, you can have those abstract names, or you can explicitly specify a list of places. So for example, in this case, we have 4 ranks, and we are saying for each rank, run them on one of these cores. So run the process on, for example, rank 0 on either core 0 or 1, rank 1 on either core 2 or 3, and so on. Instead of explicitly specifying this list, you can also give a range like this. So you go from 0 through the total number of threads that my application requires with a stride of 2, and use that for placing my process and its threads. And then once we indicate, okay, where we would like our processes to be placed, then we want to indicate how these threads are bound to resources, the OpenMP threads, right? So there are different options again. Check the implementation. In the one that I checked, we can use false to completely disable thread infinity, or we can have one of these 3 options. One is close, which I have used a lot. So this is, I want to bind the threads of my process close to the primary thread on the given places. So the places are defined by OMP places, but within those places, I want the threads to be as close as possible to the primary thread. Now, if I've given a lot of places, then, and I don't have so many threads, then please spread my threads. That's the second option. Spread my threads evenly on the given places. And in case we, for some reason, we just want to run everything on the same physical core, then we use this option, procbind equals, OMP procbind equals primary. So in this case, we will bind threads on the same place as the primary thread. One reason I can think of is that we want to use the same caches. We are very particular about that. So OpenMP specification, this also keeps changing. Please refer to it. And you know, a setting that works on one machine may not work on another. So with this particular thing, we just have to play with all the different options and see which one works for the system we are on. So the last one for serial applications, this is the one that I've used the most because I use the GNU implementation of OpenMP. And so for this serial process, we would like to set, we have 16 threads, and we are specifying explicitly where those threads will be bound. So we are giving a range of 0 through 64, but we are going to stride by 4. So in this example, we expect all the 16 threads to be scheduled on cores 0, 4, 8, and so on. Now, this particular thing is not only applicable for serial applications. Even if you have a parallel application, multiple MPI ranks, you need to have a wrapper script, but with the wrapper script, you have to set up GOMP CPU affinity for each rank differently, so that each rank and their thread and its threads can be scheduled on exactly the cores that you want. So if you're interested in an example of that wrapper script, please reach out to me. I will send it to you, because we are not showing that in this presentation, because this is not used in Lumi type clusters, where we have the Cray environment. So, okay. Now we're going to look at the example where we have to set CPU and GPU affinity. We're going to see a few examples of that. So this can be done in many different ways, depending on the MPI implementation. OpenMPI has MPI run that offers several options for process placement, order, and binding. And so for that, we refer to the MPI run documentation. Man page for it is quite good. And Slurm offers a rich set of options. Slurm binding is something that's commonly used. And mpitch does not have many affinity control options. It is better to use the native process manager, but it is possible to build MPitch with Slurm integration. So that way we can use Slurm bindings, and that's what we will do when we run on Lumi, is that we use Cray MPitch that is built with Slurm bindings, so we get all of the affinity related controls as well. So in the case where we have multiple MPI ranks with OpenMP on, multi-threading on the CPU, this is the example code that we are going to use. Okay, this is the example code that we're going to use. And I just want to point out a couple of things here. This is on the right, we see the output that this program produces. And we use this code to identify whether we got the right binding, right, to verify our bindings. And so we want to know what MPI rank we are running and which thread is bound to which hardware thread and so on, which OpenMP thread is bound to which hardware thread and so on. So to find the MPI rank, of course, it's MPI com rank, the function. And then to get the OpenMP thread, we use OMP get thread num. And to find which hardware thread we are scheduled on, we use this function sched get CPU. And in all of those different example programs, the Hello World programs, you'll see the same kind of thing. In the case where we also have to identify the GPU affinity, I refer you to this program. The link is available to you, and here I'm just pointing out the functions because the program is slightly longer to fit on the screen nicely. So we print. These are all the things that we print, and how we obtain those things is what we describe here. The output looks somewhat like this. And we already know how to get the MPI rank, the OpenMP thread number, the hardware thread, we sched get CPU. Now, RT GPU ID is the HIP runtime. When we use HIP get device, that is the number that we are printing here. The GPU ID is printing the list that rocker visible devices environment variable is being set up with. And then the bus ID, this is very interesting because this is the one unique thing that we get per GPU device. So HIP get device get PCI bus ID, that is the API we use to identify this bus ID. And this, I've used this in cases when it is not clear what device I actually got. Because ROCm SMI can give us a number. Sometimes HIP get device can give us a different number. So the only way I know which device the process is running on is sometimes by using the bus ID. Okay, so we're going to use these hello world examples. And the other thing we also want to keep in mind is this optimal core mapping with GCDs. So since in Lumi it's slightly different, the sets of cores that are closest to each GCD is different. So for GCD 0, the cores that are closest to it are 48 through 55. For GCD 1, it's the ranges are different, and it doesn't go in, it's all over the place, right? But this is the optimal mapping, and this is what we want our processes and threads to be using. Like if my process is using GCD4, then I want to pin it on one of these cores, 0 through 7. Okay, and how would I pick the GPU device for my process? That is done by setting one of these environment variables, right? By default, all the processes see all the GPU devices. So if we want to restrict visibility to some a particular GPU device for a given process, then we need to set either HIP visible devices or rocker visible devices. Now, when you use Slurm to allocate a GPU for you, that is behind the scenes, it is setting rocker visible devices, and that's the allocation that you get. There is a slight difference between these two. These two are not the same. HIP visible devices restricts GPU devices visible to the HIP runtime. So we have in the AMD software stack, the ROCm software stack, we have several runtime libraries, one of which is the HIP runtime, and below the HIP runtime is um, the Rocker runtime. The HIP runtime depends on the Rocker runtime. To set GPU device visibility on for each one of these layers, we use different environment variables. But the thing to remember is the HIP runtime depends on the Rocker runtime. So if you have restricted visibility at the Rocker level, then the HIP layer can only see those devices. And then you can further restrict GPU visibility at the HIP layer by using HIP visible devices. But this is something um, uh, just important to know. I think for Cray and Pitch uses Rocker visible devices, and for OpenMP offload codes as well, we have to set Rocker visible devices to restrict which GPU this process is supposed to be using and so on. Okay, so here we go with the first example. So how, in order to set up Rocker visible devices, one very simple way is to use the Slurm local ID. So each MPI rank has its own local ID in Slurm when run under Slurm. So we use that. Okay, so if I have 8 ranks, my ranks go from 0 through 7, and the Slurm local IDs go from 0 through 7, and I will just use the same IDs for the GPU devices as well. So I'm exporting Rocker visible devices equal to the Slurm local ID. This is a simple one, right? And so again, on Lumi, Lumi is special. At least as of February, end of February in March, we had to do a 2-step run. So we had to allocate in a particular way and then do a S run in a particular way. So let's take a closer look at these commands. First, we are going to run on one node. So we are going to allocate for the given project in a given partition this one node. And we want to use all the GPUs in that node. And we say threads per core, we only want to use one of those hardware threads in each physical core, and have all the host memory available to this allocation. I want to make it also exclusive. I believe we needed to have this exclusive option in salloc, but not in srun. So something interesting. And then follow that up with the actual run. So when you do the srun, we're going to run on one node on 8 GPU devices. And here we also say we have 8 tasks. And this is our application, the hello job step. But what I'm going to do is I'm going to run it under this wrapper script. So the wrapper script is the one that we saw here, which is going to set up GPU device visibility for each one of those ranks. And then the application is run for each rank. So this gives us an output like this. We are running 8 ranks, and each rank, because of our wrapper script, the set GPU device.sh, each rank got a different GPU device, and it also got exactly, so the rank 0 got GPU 0, rank 1 got GPU 1, and so on, right? This is what we expected. This is great. But what happened with the hardware threads? Oh, we just got a different hardware thread for each rank, but all of them are clustered in the first, in 2 NUMA domains, because we couldn't get core 0, so it went from core 1 all the way through 8, so, or in 1 NUMA domain. Okay. That is not okay. So let's look at the optimal mapping. If we are using GCD 0, we would like to be on one of these cores, 48 through 55, but we ended up being in hardware thread 1 instead, and this is not okay, right? This is not optimal. It'll run. Maybe you can get better performance if we fixed that. So here we're going to try and fix that by using a Slurm binding option. We're going to use the mask CPU option. So that is what we see here. CPU bind, this is the additional option we're going to use, equals mask CPU and use a particular mask. The mask is something that's in hex. It's a little bit difficult to read. but we have a way to figure this mask out. And I'm not sure if we have other better ways of doing this now. I'll have to investigate that. But once we use the mask, the output now, okay, we have the correct, so it's MPI rank 0. Each rank has only one thread, CPU OpenMP thread. Now it's running on core 53, and it is using GPU 0. So that's fine. That's the right mapping. And we also see that each rank got one of the hardware threads from each core set, which is also what we wanted. So by setting, so this is FE, which is we are setting, we are skipping one core and turning on 7 other cores in each core set. And so the operating system is able to schedule this one process on any one of those 7 cores for it from each core set. So that's what we see here. So how do I generate this mask? It looks wild, right? Thanks to Marcus Wagner, who helped me with this a couple of years ago. So there is a script where you can go and say explicitly specify what cores you would like for each one of these ranks, and then just running the script generates the mask for you, just prints out the mask for you. It's a Python script. It's very easy to understand. Right? In this example, we are skipping, so instead of going from 48 through 55, we have skipped the core 48, and similarly, one in each, the first one in each one of these sets. And this is all to deal with this low noise mode on Lumi. Okay, so let's take the next example. Here again, we want to run one MPI rank per GCD, but this time, instead of one OpenMP thread per rank, we have two OpenMP threads per rank. If you see, the srun command, there is absolutely no change in it. What changes is how many threads you have in OpenMP. So this OMP num threads, we have changed that to 2. And we also want these threads to be pinned to cores that are close to the primary thread. So that is another thing that we're using. We're using the OpenMP proc bind affinity controls from the OpenMP standard. So the output, let's take a look at rank 0. Rank 0, it has 2 OpenMP threads, and they both run on cores 49 and 50, which is good, the right range. And they are using GPU ID 0, which is also good. Rank 1, it uses GPU 1, and it uses hardware threads 57 through 57 and 58, which is also in the right range for that GCD. Okay, now let's take another example. Here's where this is what I was referring to earlier. Now we have, we would like to pack the entire node, use all of the resources possible. And in this case, we want to run 2 MPI ranks per GCD. So we want to run 16 ranks on this node. But because of low noise mode, we are not able to use 4 threads per rank, which would have given us 64 cores to use, but we cannot because one core is not available. And so if you want to do a balanced resource assignment across all the ranks, you have to skip one core for each rank, and you end up with only 3 OpenMP threads per rank. But that's okay. Running 2 MPI ranks per GCD also introduces a new complexity. If we want to run it in such a way that the ranks are closely packed on GCDs, for example, we want to run ranks 0 and 1 on GCD 0, and then run 2 and 3 on GCD 1, etc. Maybe, in this case, my application, the communications between ranks that are closely placed in the order, they communicate the most, maybe. And so I want to pack them on the same GCD if possible, or on the same device GPU if possible. So in this case, we have to make a slight modification for our wrapper script that sets the GPU devices for each rank, because now we need to associate 2 ranks per GCD. So we go and calculate how many ranks per node. Okay, this also extends to multiple nodes if you wanted to run the job on multiple nodes. First, you find how many ranks per node there are, and then you find how many ranks per GPU, and then use that to find my GPU and use that to set Rocker visible devices. Right? And again, using the same script to generate, the only change we made to that script now is explicitly mentioning what cores we would like to use for each one of those 16 ranks. And in this case, what I have done is because I want to have all of these threads for a given rank share the same L3 cache. Yeah, in this case, I chose to skip the first and the last core of each 8-core set. So here, I've skipped core 48, and for rank 2, I skipped core 55. So in that mapping, we saw 48 through 55 belong to one core set. So that is what I've chosen to do. And so after specifying that explicit list, the script prints out the mask that we want to use, right? And then using that mask, we just use that mask directly. When we do the S run, first, of course, we are running 3 threads per rank. And also 16 ranks on the node, so this number of tasks option changes, right? And we are using the new wrapper script to set up the GPU affinity, and we're using the mask, the different mask. Now the output is that, okay, so we see that MPI rank 0 and 1 both are using GCD 0. They're both running on GCD 0. That is great. And ranks 2 and 3 run on GCD 1. And we also see that the hardware threads are used. The process MPI rank 0 and its threads are pinned to exactly the hardware threads that we wanted for these threads. So 49, 50, and 51, etc. So everything looks good. So again, stressing the fact that when we have NPS 4, we would like to get the full CPU socket bandwidth, and we need to have we would like to scatter all the processes and threads as evenly as possible across all the resources we have, and we want to use all NUMA domains, right? In addition, in this case, we are also oversubscribing the GCD with 2 ranks. And this is possible in some applications because the GPU is not well utilized by just one when you run just one rank. So in such cases, you are able to run 2 ranks and get an improvement in performance. So I believe those were all the examples I had. And so let's summarize. In parallel applications, affinity is very important, and we saw that it involves placement, order, and binding. The importance of affinity is because we want to achieve the best performance, and that means we want to achieve higher memory bandwidth, we want to lower the latency of transfers or communication, we want to optimize communication, and we definitely want to avoid migration of processes. And use all the resources as evenly as possible. And in this talk, we saw many ways in which you could understand your topology, understand the architecture, uh, to do a very good job with setting the right affinities. You need to know the performance limiters of your application and design the best strategy for pinning. And the most important thing is you need to know the communication pattern between the processes in your application, right? And having known that communication pattern, you can choose the best placement. And we saw some examples of how to do that for different cases. If it is a serial application, you can do it this way. You can use OpenMP settings, and for MPI applications, we use Slurm bindings. Slurm offers this rich set of options, so we saw some examples of that. With that, I believe, thanks to this is a list of all the references that we used to put these materials together. And that brings us to the end of our talk. Thank you so much.
So that was a lot